So the first speaker is Mark, which is going to continue the lecture. And the topic of today is semantics of higher modality.
Okay, thank you. This is really 1 2-hour talk, so and I'm thinking I should say I have to leave tomorrow morning, so if you wanted to talk to me about it, then you should grab it today. I'm very sorry to have to leave. I hopefully tune in to some of the other talks later this week. But it's been great to be here. So let's see, what were we? So last time I talked about geometric infinity groupoids being sheaves on some set of geometric spaces, and there's no color, like the red is not showing.
Connector issue.
Okay.
It's probably the plug on the computer, because it's no red everywhere. So if you have a, yeah.
Okay, and so semantically, these sheaves form what we call infinity one topos, and so what we're trying to do is interpret type theory in this infinity one topos of geometric groups, or more generally in any one of these at all. And so I talked a little bit last time about roughly how the flat looks like semantically. But I want to start now by talking a little bit more generally about interpreting type theory in higher toposes and report a little bit of progress in this regard. So just as a review or introduction, if for anyone who's not familiar with it, there are a lot of steps in actually modeling type theory in a higher category. So type theory is some sort of syntactic object that's sort of generated by symbols that we put together according to some words. And then there's a sort of a direct categorical corresponding structure, which has lots of slightly different variants that go by lots of different names. Here are a few of them, but roughly speaking, they all play the same purpose of encapsulating sort of algebraically the structure of the syntax. And then in infinity one category, whenever I say that, I mean some without regard to how it's modeled inside of set theory, so it might be a quasi-category or a complete single space or whatever. But in general, the current technology, the way to interpret type theory into it is to present it by a core model category with some nice properties. And then we can sort of lift this structure to one of these guys by interpreting the dependent projections here to be the vibrations in our model category. And that's an amazing idea. And so there are these 3 steps here. Step 1, relating the syntax to this algebraic structure, is the initiality principle, or hypothesis, or conjecture, or theorem, or whatever, depending on your religious beliefs. So there's a lot of bookkeeping in there, and it hasn't really been written out systematically enough, but I don't think anybody doubts that it's true. It's just sort of bookkeeping. This direction here is a coherence theorem, where the problem is that it's stuck in a core model category. We can only expect to be stable under pullback up to isomorphism, whereas up here it generally has to be stable under pullback on the nose. So we use some sort of coherence theorem. So they're the older coherence theorem but more recently, Blavatsky and Blumstein and Warren and some other people, I guess, he did this too in his paper on models, have found these coherence theorems that work for basically all the homotopy theoretic information we want to strictify these isomorphisms to equalities. So the real problem that's remaining is strictifying equivalences to isomorphisms, going from the infinity one categories to the model categories. And this is where I have a bit of progress to report here. This has always been the most promising approach of taking a the injected model structure on simplicial presheets. So we were talking about presheets on some small infinity 1 category, and we present it by a simplically enriched category, and then we take presheets of simplicial sets, enriched presheets of that, as an injected model structure where the cofibrations and the weak equivalences are level-wise, and then we can take some Gaussian localization of that, which is left exact, and we can present any infinity 1 topos in that way. And this model category has been known for many years to have nearly all the structure that we need to interpret type theory. So specific types and pi types and NA types and higher inductive types. The progress that I have to report is this, that I can actually, I think, also get strict univariate universes in all of these models. So we were able to do it in some cases before Blavatsky's first model was in simplicial sets themselves when C is terminal. We made a little progress over the years, but I think I can do it in all these cases now. In particular, not just that we have universes, but they're closed under the pi types and the sigma types and the identity types the way we expect inside of type theory. The closure of the universes under the higher inductive types is still sort of open. I have some ideas about how to deal with that, but I'm not going to make any claims at the moment. I'm going to make a claim about the universe. So what I really want to do is I have some time left to talk about semantics of modalities and spatial type theory and stuff like that. And we'll see how much time I end up with, but I want to spend a few slides giving you a brief overview of how this works. And I'm hoping to put up a few things in the next few weeks or so. And some people here have already read it and given me very useful feedback. So I'd like to thank all of them for sitting in the audience. How does this theorem go in general? So let me first summarize how it works before we get to the universes. And so this is been known for a while. So the cofibrations here are monomorphisms, so they're stable under pullback. It's a right proper model category, so weak equivalences are stable under pullback along vibrations. So that means that basically cofibrations are stable under pullback along vibrations, and that's what we need to interpret identity types by path objects, as Michael suggested, and as well in his first model. Continue to do it that way. The reason you need to be able to pull back, right, so the identity types are the path objects. The reason we need to be able to pull back on vibrations is we need to be able to extend the context and still have an identity type. It's locally Cartesian closed, and these pullback stable properties tell us that the right adjoints to pull back along the vibration preserve vibrations and basically vibrations. So that tells us how to interpret pi types. Pi out of vibration along the vibration with another vibration. Sigma types are just composing vibrations, so that gives us all the basic type operations. And then higher inductive types is less obvious, but Peter and I did that in our paper by sort of taking the ordinary free algebra construction on a no function and mixing it with type replacement in an algebraic way to make it still have this right property. So I'm not going to say any more about that. Again, this is all in the level of step 3 here. So we're taking our homotopy stuff and presenting it by things that happen after isomorphism. I'm not saying anything about this certification step. Basically, all works the same way.
Sorry, can you say what was the previous stumbling block?
So the stumbling block is actually having a universe. So an infinity 1 topos has object classifiers, which classify all small objects up to equivalence. And those objects, that object classifier can be presented by some vibration in the model category, which will be univalent. It's not a univalence axiom, but it won't be closed under sigmas and pi's and identity types up to isomorphism in the model category. And so that means we won't be able to strictify it to be closed up to equality under the coherence theorem. So what we need is a small vibration such that every other small vibration is a pullback of it in a strict 1 categorical sense. So that's the obstacle.
Right. What did you make it work?
Well, so I have 3 more slides that I'm going to tell you roughly overview how this works. Okay. So the injective vibrations, by definition, they're maps that have the right lifting property with respect to pointwise acyclic cofibrations, and this is extraordinarily unhelpful. for telling you how to construct the universe. So there are particular cases where we can do a more explicit description in this way. For instance, in superficial sets, we can say what they are. They have the horn lifting property. If we take free sheaves on some direct category, or more generally some kind of nice reading category, we can describe it explicitly. But in general, this is not a helpful description. So instead, what I'm going to do is I'm going to describe the injective vibrations in a different way, which is not by giving them lifting property. You might say it's an algebraic description of the injective vibrations. And this is how it goes. So suppose I have a pointwise vibration here in this special Cauchy category. There's this thing that I'm going to call the relative pseudomorphism classifier, which has this universal property. There's a bijection between strict natural transformations from anything else to this guy are equivalent to homotopy coherent natural transformations into X whose composited Y is strict. So if you, in a particular case when Y is terminal, this is just a classifier. I guess I really want to call it a co-classifier, but I mean, you can argue about what should be classified, what should be a co-classifier. It's the things that map into it classifies. In the case when Y is terminal, it just classifies all of this they call homotopy coherent transformations. Now, I'm not defining for you what I mean by homotopy coherent transformation. And in fact, you can basically just probably the most efficient way to do that is to write down an explicit definition of this guy and then define a homotopy coherent transformation to be a map into it. The definition of this guy is what's called a Cobar construction in classical homotopy theory, if you're familiar with that. And also, if you know some two-category theory, then you may be familiar with the prime construction on algebras for a two-monad, which is the object that maps out of it classifies pseudomorphisms of algebras. And so this is the dual, the map into it classifies pseudomorphisms of algebras. There's sort of an infinity-dimensional version of that two-categorical thing. So basically, you build some co-simplicial object such that like the maps into the zeros in the zero level give you sort of components of a natural transformation. And then if it were sort of literally an equalizer of the first two co-face maps, it would be strictly natural. But instead, you glue in a homotopy there to put in a homotopy in those naturality squares. And then at the next level, you glue in a simplex to make these sort of naturality, homotopy commutative naturality squares commute up to a higher homotopy and so on. Does that sort of give some rough idea?
Are there any cases where it's sort of obvious what these are? Like what an example of a relative pseudomorphism classifier, like I don't know, in bisimplicial sets or like bisimplicial spaces or something?
Not really. I mean, you might. I mean, maybe, but to me, like the explicit thing that I work with is the description as a totem of some co-simplicial thing. And so you could work that out more explicitly in some cases.
Okay, I guess what the co-simplicial thing is?
It's a Cobar construction. I mean, you want to write it out. So you've got. So here's your category of simplicial free sheaves, and here you take your.
Can you show the blackboard a bit better?
Objects. So our family is a simplicial sets indexed by the objects, and that has a right adjoint. It also has a left adjoint, which you use for the dual construction that you're looking at the right adjoint. And then your co-simplicial object looks like GUX maps to GUX maps to GUX, and so on.
When just a quick question: under what conditions does this functor category with under what conditions do you have that pair of adjunctions?
Any functor category with this is simplicial sets, so it's completely
Okay, that's all you need.
Yeah. Any suitable functor category is both monadic.
I heard about this like 2 weeks ago and I was really surprised, but I didn't know reference.
For it to be comonadic?
Yeah, for this thing to be monadic.
Let's check.
Okay.
Wild card.
Yeah, I would call it folklore. So this is, you basically take this comonad up here, and it's a comonad simplicial comonad resolution. and then the total of that is the globe, the absolute one where y is a point, and then you take it, you pull it back to y, and you get you the result. Okay. Any questions? Okay. So the characterization is that a map is an injective fibration if and only if it's a pointwise fibration, and the map from X to its this classifier has a retraction over Y. So in two-categorical language, these are the co-flexible objects. So what this says is that if I have a coherent natural transformation whose codomain is X and which is strict in Y, then so that gives me a strict map into R of X, and then I can map it back into X. I can rectify a coherent natural transformation to a strict one in some suitably sort of coherent way. So that's what this structure. So I'm not going to say anything about how to prove it, but if you you can ask about it later.
Sure.
Yes.
Just to check, the
Yes.
size, is it sufficiently enriched, or is it just a one category?
C can be sufficiently enriched, yeah. So you can get any. So I mean, actually, I can probably say in words. Maybe one way to express the idea. You have your pointwise fibration, and you want to lift it against the pointwise acyclic cofibration. So at every particular object of C, you can find a lift because in special sets you can lift your acyclic cofibrations against your fibrations. The lifts aren't natural, but they're natural up to homotopy because they're unique up to homotopy. And so you sort of piece those homotopies together into a coherent natural transformation that is the lift, and then you use this retraction to rectify that to a strict. It's basically the expression for how it goes. And conversely, if it is an injective fibration, then this canonical map here is an acyclic cofibration, and you can lift against it and get a retraction. So there's this sort of algebraic characterization. If you're familiar with this sort of newer version of like algebraic refactorization systems, Poland, what you would call it, and this is you can think about it in this way. What I actually want to do is not quite all the way algebraic. What I want to talk about is what you might call semi-algebraic injective fibrations. So it's a map that has the property of being a pointwise fibration, together with the structure of a retraction for this pseudomorphism classifier. Now I'm going to define a universe using these things. Okay, so in a pre-sheaf category, there's an obvious way to define a universe of some kind of fibration, which is to say, well, I'm defining a pre-sheaf. I have to define its value at each object. So I'll define its value at each object to be the set of fibrations over that corresponding representable. If you say, well, that's what it has to be if it's going to classify these things. And that's what Blavatsky did, and that's what we've all done in these other models. So I'm going to do the same thing here, except that I use this algebraic structure here. So U of C is the set of small semi-algebraic injective fibrations over that corresponding representative. And you need to muck around and make this make sense. You have to choose an inaccessible cardinal, but they're too small. You have to choose sets of representatives for your isomorphism classes to make it a set, and then you districtify it somehow to make it a strict pre-sheaf lending in sets rather than lending in like groupoid or something. But I don't want to say any more about that. The important point is this semi-algebraicity here, or the structure of these retractions, because the problem with doing this is that when you define this, you define this its U like this, and then you get sort of some universal map over it, which has the property that whenever you pull it back to representable, you get a vibration. But this universal map may not itself be a vibration in general. That's the problem. And it works in simplicial sets because to test whether something is a vibration, it's enough to lift it against the generating acyclics, and all the generating acyclics, the Horn inclusions have representable codomains. And so it's enough to know that I can pull it back to a representable and get a vibration. Now, so in general, I don't have that property, but what instead I have is this structure of these retractions, and the pullback from one C to another C in this universe is algebraic. It preserves this algebraic structure. And so what that allows me to glue these vibration structures together to show that the universal map is also a vibration. It also has this semi-algebraic I can say more details about that later if you want, but that's the basic idea is this algebraic structure. It characterizes the vibrations, we can glue it together to make a universe. So that tells us how to make universes in simplicial, the injective model structure on simplicial presheaves. So that presents these presheaf infinity topos. Now we want the sheaf ones too, so we have to look at these left exact localizations. Here we use this result by some people sitting in this room, if we that characterizes the families, the localizations that are left exact. And so if you go read higher topos theory, Lurie defines a subtopos or the infinity one topos to be a left exact accessible localization. But it doesn't tell you what it is that makes the localization left exact. It's sort of a global condition that you sort of have to check. What these guys have discovered is that you have some small set of maps. There's an easily checkable property of that set of maps, which is sort of local and only refers to those maps, which is sufficient to ensure that the localization is left exact. It's basically that it's closed under diagonals and pull back to generate it, depending on how you phrase the localization. But the point is that this property is preserved by pulling it back to slice categories in an appropriate sense. And that allows us to take an external left exact localization of this topos and sort of do it fiber-wise to get an internal accessible lex modality in the internal type theory, which is sort of importantly, it's accessible and it's lex inside of the internal type theory, which is a priori is a stronger statement than saying that it's left exact externally, because again we're talking about all slice categories when we talk about these modalities inside. And then that means that we can apply this theorem that if I have an accessible lex modality, then the universe of modal types is again a modal type itself. So the sum over the universe of the things that are modal. And so then this thing can play the role of a universe in the subtopos of the sheet. Okay, so that's my 4-slide summary of that. So again, yeah, I'm happy to talk more about that later, but I also want to spend some time on the modalities. So last time we were talking about flat, well, I wrote these slides. We're talking about a one site, just because most of the examples are one site, but I think probably most of this can be generalized. So in general, if we're looking at this some sort of presentation of this sheaf topos with limited model categories, then if as was mentioned before, we get this thing here sitting over some little sets, or this sort of a presentation of the infinity topos version. And so we have this discrete inclusion, and then it has a left adjoint and a right adjoint by con extension. And in addition, if this site has a terminal object, then this the right adjoint, the limit here, is the same as just evaluating at the terminal object. And so it has a further right adjoint, which is sort of takes the power by the global points of the set. And so this here is the thing that acts like discrete things, and this thing acts like discrete things. This left is the discrete inclusion and the co-discrete inclusion are fully faithful, and they're mapped from one to the other. In terms of the HoTT theory, this discrete thing, which is just a constant presheaf, it preserves configurations and weak equivalences because those are just level-wise in the injective model structure, and so in particular they remain so in the localization. So that means that this discrete global sections adjunction is equivalent. But if this composite comonad doesn't preserve vibrations, so we had to vibrantly replace it to get it flat in the internal type theory upstairs. So that's what I described yesterday. I wanted to add a caveat to what I said yesterday, which is that I'm not presenting a formal syntax semantics for this. Exactly what we mean by the version of sort of categories with families or whatever in the modal case is something that people are currently working on. Dan and Mitchell and I are thinking about it. Colin's thinking about something related. And so this is what I'm just presenting here is just an informal sketch that is sort of motivating for the rules of type theory. Yes?
basic question. So, not all things are cohesive. But you say, okay, just take one side of internal object, I get all these adverbs. So, what is the condition that fails like the word?
Well, what I'm describing here, this is just at the point set level. And this left vocalization here doesn't change the category, it only changes the model structure. I mean, this is sort of all true of the pre-sheaf topos. And the pre-sheaf topos on a category where the terminal object is cohesive. So this is sort of the pre-sheaf level cohesion. I haven't said anything yet about how it relates to the sheaf.
Okay, right.
That's a good question. The sheafification or localization structure comes in when we start talking about sharp. Okay, so sharp is about this other adjunction, this composite of lower star with upper pound or whatever that is. It's not quite the same as sharp, right? So this adjunction is not always equivalent for the localized model structure, but it is if the terminal object has no non-trivial covers. That's what tells us that this global section considers these equivalences. You can do this with some like classical localization argument. The covers are just isomorphisms on spaces of global sections, and so that's enough to tell you that this thing turns out to be equivalences. So we get this right equivalent adjunction, and that tells us that this here this triple at least descends to the infinity one categories, and we get a local infinity one topos. So with global sections, geometric morphism has a further right adjunct. And in this case, the sharp is supposed to be this composite here of the global sections with the discrete, the co-discrete functor, and that one preserves all fibrations already, so we don't need to replace it. And this is my intuition, at least, for why in describing sharp inside of the type theory, it behaves differently from flat, in that it's sort of it's like a negative form, and it has a sort of a strict judgmental uniqueness in addition to computation. So let me go back now to the type theory and talk about sharp. So sharp was already used earlier this morning, but I didn't get a chance to mention the rules for it yesterday. Syntactically, we can think of it as dual to flat in the same way that function spaces are dual to Cartesian products. I want to say exactly what I mean by that, but there's some sort of intuition there. Like it's sort of right adjoint in some sense, and in the same way, they both sort of internalize some judgmental structure here. They both internalize the crisp variables here by putting a flat on the A, or sorry, these should be C's. Here, or by putting a sharp on the B. In the same way here, we sort of put times on the left with an arrow on the left. So semantically, what's going on here? The rule for yes.
Could you go back one second? Why is the C?
Yeah, that's a mistake. That's a typo.
Okay.
These B's and C should be the same downstairs. The rule for introducing a flat said that anything which is cohesive in the context where we're trying to introduce the flat gets ignored when we talk about when we are going to enter the flat. Sharp has sort of the dual property that everything that's cohesive in the context gets treated as if it were crisp. The way that works semantically is that so this hypothesis of introducing a sharp says if I have A that depends on both delta and gamma crisply, so that means I have a fibration over P star of gamma, which lives over P star of delta. I mean, so remember, gamma is a cohesive thing. It's a vibration in our sheaf topos model over some discrete object. I can apply P star to it and get something over that, and then A is only required to live over here. But then I can apply P pound P lower star to that, and because these things are fully faithful, these things in the middle disappear. So I get this chain of vibrations because P lower star and P upper pound both preserve vibrations. And so then I can pull this back along this map from P upper star to P upper pound and get gamma maps to this thing, to its co-discretification. I pull this back, I get sharp A living over gamma itself. Even though A itself, A lived only over P star gamma, sharp A lived over gamma. So I have this thing in the cohesive context here, even though it was only crisp in the premise. And the same thing happens for the introduction rule. That this map up here is the upper sharp that maps from A, which is sort of a crisp element of A that depends only on crisp context, and it maps into sharp of A, which is related as cohesive context. So just like inside flat, the cohesive variables from outside are invisible. Inside of sharp, the cohesive variables from outside can get treated as if they were crisp. And then the elimination rule is basically this thing on here, or sort of more precisely, we apply p lower star to it, and all the horizontal arrows get inverted by p lower star, and so sort of everything gets collapsed once things are crisp. And so that tells us that if I have a crisp element of sharp A, that's basically the same as having a crisp element of A. And so this lower sharp sort of takes a crisp element of sharp A and extracts an element of A, and these sort of things are inverses sort of strictly because everything was sort of twice more crisp and we didn't need the vacuum to replace. So that's the sort of homotopy theoretic intuition for why it's sharp is yeah.
I have a question.
Yeah.
So here you write A lower
sharp.
So earlier you wrote upper sharp.
Yeah, they're two different things. Right, so upper sharp is the introduction rule, and lower sharp is the elimination.
Okay.
So the upper things are the introduction rules that live in the sharp or the flat, and the lower ones get out of it back to something else. But the rules for what's cohesive and what's crisp are different. So since sharp and flat are sort of introduced by these rules that both sort of internalize the crisp context in different ways, we can prove all the stuff that we expect to be true if we have an adjunction and so on. Here's if I apply sharp, then that's the same as applying flat and then sharp, or if I apply flat, that's the same as applying sharp and then flat, because both of them are basically saying, take the underlying infinity groupoid and then make it the discrete topology or the indiscrete topology. You can sort of muck around with these upper and lower things and make sure that sort of everything is crisp when it's supposed to be, and then calculate that these things are inverses. So you can prove that these things are left exact modalities. Sharp is a monadic and flat is a comonadic. They both sort of preserve identity types in these senses. For flat, it's different because these things have to be crisp and you can apply flat in this context. And flat and sharp are adjoint to each other when I stick an extra flat on the front. Because if you sort of think about it topologically, the space of maps from flat A to B and the space of maps from A to sharp B both have the same points. They're both the maps from A to B that don't respect any of the geometry, but they might have different geometries themselves because this one sort of has a co-discrete geometry induced from sharp B, and this one has the ordinary geometry induced from B. So I have to flat them or sharp them in order to make them equivalent. But once I do that, then I can prove that they are there.
So
Yes.
on the semantic level,
They're adjoint external. They're adjoint as functors, finger functors of the topos.
they're not adjoint on the level of index.
They're adjoint as indexed over the base topos, but not indexed over the top. The flat is not even an indexed functor over the top. That's the semantic version of this. So that's with the flat and sharp is what I call spatial type theory. I don't know how good of a name that is. I kind of wanted to call it local type theory because it corresponds to the local toposes, but local means so many different things that I just thought that would be fun. I'm like, well, you got a better name? Maybe there's a better local topos type. Right, so cohesion is what happens with this further left adjoint, the P lower street. Again, in the pre-sheet world, we have this, which is just the colon functor. But when we add the homotopy theory, there's basically no chance that this last adjunction is ever going to be a colon adjunction. this functor, this upwards functor here that it makes a sequential set into its constant presheaf is almost never going to be injectively fibered. It's projectively fibered, but we're using the injective model structure. We could fiberly replace it, like we did with flat, to get a model of the shape of X. But that would have the problem that would clobber the context. That would mean that we would have to also apply shape to everything in the context. And that might sometimes be what you want, but it'd be more useful to be able to apply it in more general context without messing with the context. And so in this case, what we can do is construct it internally by nullification. So I mentioned that before, that we can nullify at real numbers or our line type A1, which we mentioned in other talks too. But I wanted to say a little bit more generally the conditions on the site which make this work. So I attributed this to Lewis. I guess the similar ideas for one topos are there in Brouwer's work. Just gets to an elephant. Anyway, so we already talked about having an irreducible terminal object. So not the terminal object doesn't have has no non-trivial covers. That's what gives us the right adjoint that makes sense homotonically. For the left adjoint to make sense, we want the site to have finite products, or I guess more generally, be co-sected. We want the covering sieves to have retractable nodes. So this is the sort of the Groganic topology way of saying that our local geometric models are locally contractible. So, I guess our models are contractible, so that our spaces are locally contractible. When this is true, then you sort of muck around with what it means to be discrete, and you get an internal characterization. So discrete is saying that it's basically constant homotopically as a presheaf. So the you map the x of d is an equivalence. But since we have a terminal object, that's the same as saying that x of 1 to x of n is an equivalence. And more generally, I can talk about the image of any product projection being an equivalence. But now this, if I sort of think about, if I apply the innate element to this, that basically what that's saying, if I fix v and let u vary, what this is saying is that the map of presheaf from x to the internal Hom presheaf from the representable on v into x is a level-wise equivalence. And I can, it's enough to restrict v to some set of objects that generate the category of their finite products. And so often that's going to be like the real numbers, continuous real numbers, or smooth real numbers, maybe an outline line or something. It won't always be just one object that I'm going to take some multiple objects, but whatever they are, I can take all the objects in the site, and that's certainly good enough. So then internally, I can say that I have a family of objects which characterize the discrete types as the null types for those objects. And so we can construct the shape by doing this internal hierarchical nullification that gives us this left adjoint. So this is the semantic version. And the conjectural semantics for this is in cohesive infinity one toposes, or which are also called local and stably locally connected, or strongly infinity connected, or I should say contractible, or something like that. Basically, they're the ones where we have this adjoint string at the infinity level, where the left adjoint also preserves finite products. So Brouwer talked about things related to these in the one topos case. Johnson characterized the sites that give rise to them, and then there's proved that this extends to the infinity case. I say this is conjectural, mainly because we don't certainly know how to build the algebraic model type theory in this case, like the category with families or whatever that corresponds to the model thing, actually making precise this on top of the condition. But as I said, this is sort of the idea of what we get by modeling geometrically contractible spaces. So in particular, we have continuous infinity groupoids, where we take Cartesian spaces and continuous maps and open covers, which gives us cohesive type theory. This site is generated from the products by the real numbers, of course. And the amazing thing that happens in this case is that this representable object can be constructed internally in the type theory of this topos as the Dedekind real numbers object. So I define inside the category, I have the natural numbers, I define the integers and the rational numbers, and synthetic sections, and I get some object which is equivalent to this representable. And so I can express this axiom here, not rather than by saying there exists some unspecified family. I can say this family, I know what it is. It's the real numbers object that characterizes the discrete ones. But let's see. So this condition here, I mentioned this already. So that the axiom, so this is what I call axiom C0 here, that we can construct the shape by nullifying at some family of objects. This axiom here is stronger because it says I don't just have some family, I have the real numbers, but in between there I can assume extra things about my generating family. So if I assume that my generating family of these types are all inhabited, then I get this stronger condition that which is sometimes Johnson calls punctual local connectedness or local contractibility, and Chris calls it pieces have points, or points pieces have points, right? And Brouwer calls it something else, the no Shulman signs, I think. So basically, that every connected component has a point in it. Yes.
So there's nullifying. Right, you have the things that are null, and maybe you want to localize it that somehow.
You're localizing at this family R,
Right.
and so that means you're building a reflector into the subcategory of null things. So the null things, which are the ones which think all these things are contractible.
With how suspending, is it just easy to do internally?
Well, Egbert described it on the first day. You write down.
I wasn't there.
Okay, you write down a higher inductive type. Basically, you say, given a type X, I define a higher inductive type which has a map from X and which is R local. Like every map from R into it, I give myself a point which says being constant. But that's okay. It's you can read about it in the So the stronger assumption that all these types have a point implies internally and semantically you sort of expect that it should be equivalent by finding a suitable site to this condition on regulating flat shape. And then there's a stronger assumption that there's one of these generators which has two different points in it, which is of course true of the real numbers and this sort of, and that again implies it should be equivalent to this condition about the shape of the co-discrete things. So what do you think? What do you think? Think a moment for about what you expect the shape of something co-discrete should be. So something co-discrete is you might have a lot of points, but they're all stuck together with geometry in sort of a unique way. And so now the shape, it says if things are stuck together with geometry, then I should identify them with homotopy. And so shape of sharp of something should be means first I stick everything together with geometry, and then I make all the geometry into homotopy. So that should be the same as sticking everything together with homotopy, which is the propositional truncation. And that's what this axiom tells us that intuition is actually correct.
So is it sort of like the risk completion a little bit? I mean, you have things that are identified algebraically, and then you identify them with homotopy.
I don't think so. Device completion is a modality on the topos of bisequential spaces. Or device completion or the seal space, single space completion. But I don't know if I get relates to the sharp this way.
You also have cohesion of categories.
What?
You also have cohesion of categories. I'm just.
Yeah. So the model of simplicial infinity groupoids is cohesive because it's a Cauchy or whatever, so it's local. But the co-discrete ones are the sort of the co-skeletal things, and the discrete ones are sort of much more constant, and the shape is like the colon of the geometric realization. So that maybe I think that does have this property, but it's not. That shape is not the best completion. Okay. So I want to say a little bit about some examples of how we could use this cohesive type theory to say interesting things relating geometry to or topology to homotopy. So we've seen lots of examples of this sort in most other talks, but I wanted to talk about the first examples, particularly in the case of real cohesion, where the shape is localization at the internal Dedekind real numbers. Because this example, first of all, it tells us things about classical topology, which is interesting to me because I sort of started out as among other things an algebraic topologist. But it's also interesting because inside the type theory we can use constructive analysis because we have this world of constructive logic, and we're working with the real numbers, which are the Dedekind real numbers that are constructed internally. And so we can use ordinary sort of constructive analysis with those and say things about, and then connect it with shape to synthetic homotopy theory and get information back out about these real numbers and sort of spaces built. So here's the first proof of concept example that is in my paper introducing this stuff is Brouwer's fixed point theorem. So this is the theorem that if I have a continuous map in classical mathematics, a continuous self-map of a disk, then it has a fixed point. So this is the simple two-dimensional version. Here's the standard classical proof that uses algebraic topology. Suppose we have a map with no fixed point, then given any point in the disk, f of z is different from z, so I can draw a line from f of z through z, and eventually it'll hit the boundary. And that function mapping z to this point r of z on the boundary is a retraction from the disk to the circle. Because if z were already on the boundary, then it would already be there. I would have to go any further. So z would equally r of z. So that means that I have a continuous map R, which retracts the disk onto a circle, but that's impossible because the circle has a non-trivial fundamental group and the disk does not. And so I can't possibly have it. Right? So this is one of the standard classical applications of homotopy theory to say things about topology, right? Because this fixed point thing is up to isomorphism, or I'm sorry, we're working with spaces up to isomorphism, we're working with points up to literal equality. When I say fixed point, I really mean a point that z is literally equal to every z. But at the same time, we're using homotopy theory to say things about it. So ordinary non-cohesive homotopy type theory doesn't really have a way to access this sort of application because our circle, our homotopical circle, we can prove synthetically that pi1 of it is z, but we don't have any way to relate it to a topological circle to be able to apply this. So with real cohesive type theory, we can try to do this. So here's the first try at writing this corresponding proof. And the first thing to notice is that I've crossed out the words continuous because we're in the world of cohesive things where everything's continuous. The next thing to notice is that the only real change here is that now I applied the shape operator. And so we construct R. We don't have to check that it's continuous because by definition it's a map in our world where everything is continuous. And now I apply the functor shape to it to tell me that shape of the circle of the topological circle is a retract of the shape of the disk. But we know that gives us a non-contractible type, that this is the homotopical circle, which is then a retract of the contractible type, which is impossible. So it seems like it should all work. The problem is that we're sort of using a little bit too much classical logic to be in constructive analysis. So first of all, it's a proof by contradiction of a positive statement. So we're trying to prove that there is a fixed point. We do it by assuming there's not a fixed point and getting a contradiction. In classical mathematics, that's fine. In constructive mathematics, it doesn't work. We have to be in constructive mathematics in these non-classical toposes. There's an additional problem, which is a little bit more subtle, but if you're used to thinking about constructive analysis, you might notice it. In order to draw a line from f of z to z constructively, it's not enough for them to be not equal. I need them to be apart from each other at some positive distance. I mentioned this in a question this morning. But my assumption for contradiction only tells me that they're not equal to each other. So the way we fix this is sort of basically by fiat. David mentioned before this excluded middle axiom, which is true. So I remember I just said our toposes are not classical. We don't have excluded middle, but we do have this as long as we build them from a classical base, we start from like classical ordinary infinity groupoids, then we build our cohesive things from that, we get this sort of flat or sharp or crisp excluded middle, that if I have a crisp proposition, then it's either true or false. Or you might more generally, if I have a discrete something flat up front, then it's either true or false. So if I have a crisp proposition, then I can use proof by contradiction on it. And then we deal with this other thing also by fiat. We just suppose that inequality and apartness are the same. And as David pointed out, it's true in these models, in this particular model, that these are actually the same, although in general, constructively they're not. And so with that slight fix, this there does work. So we use this flat that's in the middle, and I call this the analytic Markov's principle. This was a word sort of suggested by Tony Bartels. The idea is that if I say this for the Cauchy real numbers defined as equivalence classes of Cauchy sequences, then this statement for Cauchy real numbers is equivalent to what we call ordinary Markov's principle. That if a computation can't fail to halt, then it does. But this is a statement for Dedekind real numbers, but that's what we call it, the analytic Markov's principle instead of the Cauchy. So in this case, it does work, right? The only change we have to make here is that this function here we assume as a crisp hypothesis. So f is crisp function from d to d to d 2. So f is still itself a continuous function because it's an inhabitant of this type, d2 arrows d2, which is the space of continuous functions. But f is a crisp element of this type, which means that it's an element of the underlying set of the space of continuous functions. And so it is a continuous function, but the construction doesn't depend continuously on f itself as f varies. So now we can do proof by contradiction because f is crisp, and so the statement is crisp. And then we use the Markov's principle here to say these are actually apart from each other, so we can draw a line, and then we apply shape and the topological meaning of this, the fact that this hypothesis is crisp, as I said, means the fixed point doesn't vary continuously with the function f. And if we think topologically, that's exactly what we should expect, because the reason that a fixed point theorem like this fails to be true, fails to be just blanket true constructively, so a topological reason for why it fails to be true, is that precisely that the fixed point can't be chosen to vary continuously. We imagine a function which sort of squishes everything down towards a point over here, then you can imagine deforming that function just a little bit, so it suddenly deforms everything to a different point over here. And so this is the fixed point. So fixed points don't vary continuously in function. It's the same reason that the intermediate value theorem is not true constructively, because the point where a function crosses a line doesn't vary continuously as we deform the function. It can sort of slide up and like suddenly the crossing the zero will jump from here to here. So that's what this crisp assumption, the fact that we can assume that to be a crisp element, allows us to get around that contradiction. What? 7 minutes? Okay, that's a lot. So the last example that I wanted to mention is the one that David mentioned, that we can prove that every function is continuous internally. So this is sometimes called Brouwer's theorem because he proved it in constructive mathematics using his axioms of property and choice sequences. But here we can prove it using these Elimination Rule principle and the cohesion modalities in real cohesion. So here's a really brief sketch of the proof. So we want to prove we have a crisp function. We want to prove that it's epsilon delta continuous. So any crisp element, any of the real numbers, right? So A is crisp, F is crisp. Given an epsilon, we can assume that epsilon is crisp too, because it may as well be a rational number, and the rational numbers are discrete. So they may as well all be crisp. So now I'm going to define a couple of subsets of the real numbers. So U is a collection of things whose image under F is epsilon close to A. And B is the collection of things whose image under F is epsilon over 2 far away from A. Okay? So we can say constructively that every real number is either less than epsilon or greater than epsilon over 2. That's a sort of disjunction which works in real numbers. And so R is the union of this type U and this type V. In other words, R is the push out of U and V under their intersection. Now, shape is a left adjoint, so it preserves push outs. So that means that the push out of the shape of U and the shape of V under the shape of their intersection is the shape of R, which is contractible, because we're in real cohesion, so R generates the shape. Okay. Now, David already talked about connected components. So A is an element of U, right? Because F of A and F of A equal to each other, so the distance is 0. So A lives in U, and it has a connected component, by which I mean, as David did, the fiber of U over A in the image of A in the shape of U. So think of the shape of U or this shape 0 of U, maybe, as the set of connected components. The fiber of that is the connected component of A. In this push out, this element, this connected component here, which lives in here, has to get identified with things over here in the shape of V in order for the component, for the push out to be contracted. As long as so we have to sort of futz around with F to make sure that V is non-empty. But we can sort of do that by modifying F very far away to make sure that without changing it near A or changing its continuity, to make sure that there are some points in V. And so the fact that this point in the shape of U has to get glued together with something in the shape of V, that tells us that this push out has to be over something non-empty, something inhabited. Because if I push things out and get something contractible, I have to be I can make some argument about homotopical push out, which is sort of like a very, very baby Van Kampen theorem, or very, very baby Weigert-Massey theorem, to say like if two things get identified in the push out, then there must be something up here in the thing that I'm pushing out of, whatever it is. So there must be a point in V, which is also in U0, in the component of A. But since it's in V, it can't be equal to A. In fact, it's got to be apart from A, because it's in V, its distance under F is far away. So now we've got A, and we've got a B, which is where such that F of it is in both U and V. And so A lives on one side of B lives on one side of A. I can find something on the other side in sort of a similar way by sort of looking at what happens on one side. But U0 is connected, because it's a connected component. So it includes everything in between these two B's that are on either side of A. And so that means there's some positive distance delta, such that everything that's less than delta away from A must also be in U. And that's what we want. So it's continuous. Yeah.
Where did you use A and P?
Here. So you could equivalently assume that F is strongly extensional. So I have a point of B such that, so that means that F of X is apart from F of A. And I want that to use that to conclude that X is apart from A. Right. And so if I just have an arbitrary function, that doesn't necessarily reflect apartness, but under A and P it does, because apartness coincides with this equality.
Could you say again, what is this, how you concluded that B must be far away, or must be there, must be inhabited?
Let's see. So there must be some point in here. I can modify F to make sure that there's some point in V, very far away.
Okay, yeah.
But then I have A, which lives in here, and I have this other point in V. But this push out is contractible.
Because then V might be empty.
No, V can't be empty. I say I can modify F to make sure that V is not empty.
But F could be constant.
Right, F could be constant, but I can modify it to make it non-constant. Okay? Because I'm only interested in what F does near A, in order to show that it's continuous. So I'll just say way over here, I'm going to change F so that it does that. And that doesn't change whether or not F is continuous, but it allows there to be some sort of
weird.
Okay, yeah. That's kind of weird.
Somehow the behavior there, which is not.
Yeah. Okay, 1 minute. Great. I'm So there has to be a point which is far away, so there has to be something in the intersection here, and that intersection, in my opinion, is close to B. So I find this really amazing because it means that this formal setup of cohesive type theory with these adjoint modalities and this idea that these two axioms uniquely determines the epsilon delta notion of continuity. In some sense, we started from the epsilon delta notion of continuity to build the model that motivated us. But once we've got this formal type theory, then the epsilon delta notion of continuity falls back out again very automatically. Namely, the flat of the type of endomorphisms of the real numbers is internally provable to be the subset of continuous functions in the epsilon delta sense from flat of R to flat of R in the discrete. So that's probably a good place to start.
Thank you, Mike. Yes, Steve.
I just want to call attention to the fact, for those of you who didn't quite get it, that Mike just announced a really important result that's been open for, I guess, 10 years. So, yeah, it was conjectured by me in a paper that started circulating in 2009. Okay. So, and then there was a discussion of it even at Oberwolfach in 2011, where I guess we agreed that, well, so the question is whether HoTT interprets into every infinity topos. That kind of can be an internal language for any infinity topos. And over Wolfach, it was agreed that, well, probably locally Cartesian closed quasi-category, yeah, we can do that in type theory. And Andre Joyal, I think, stated that quite precisely. And that was worked out pretty quickly, but then the remaining important bit there, the univalent universe, and over Wolfach, I won't name any names, but it was said by very competent people that no, univalence is a special property of simplification. Yeah. And it's not going to happen that that's going to be interpreted in even other pre-sheaf. So it's a really important fact, and it was a very much a non-trivial fact. It's been open for a long time. It's hard work. I think it's a great piece of work, and it's a great confirmation for the research program. It really gives us a boost. Thanks for that, Mike.
Other questions going on?
Yes.
In constructive analysis, there is an approximate version of the Brouwer fixed-point theorem.
Yes.
Do you have also a version of that in your system?
Yes. So this version here uses these classicality axioms, and so it gets a sort of a crisp version of the classical version. But you can get rid of these classicality axioms and then prove an approximate. It's not completely satisfying because I don't know how to get rid of the crispness assumption on that. Because in constructive analysis, the approximate intermediate value is just provable. Right? You don't need any sort of crispness and modalities or whatever. But using this technology, I don't know how to prove it without the crispness. We can get rid of the classicality.
It also doesn't hold for the exact same reason you said. It doesn't hold not crisply, right?
The approximate one does.
Oh, but you have this example where you form like a function, something that fixed point does.
Yeah, but the approximate fixed point can move continuously. Because if the fixed point jumps from here to here, that means that it's sort of.
More questions?
Yeah. So you start the whole set with chart, but naturally I'm interested in non-coherent places. So what depends on having chart? I mean, I read a paper and sort of the part was independent of this, or just what JSON.
Yeah, that's where I get the
Right.
But not. So now
Yeah.
something snappy that you use.
So in the paper, I used Sharp to prove some important properties of flat, but those properties of flat could alternatively be assumed by themselves. And so one property like that you want to be able to use path induction on a crisp path or identification. And you want to be able to destruct something belonging to a coproduct or natural numbers in the crisp context. And you can prove that if you have Sharp, you can prove that from the otherwise. But if you don't have Sharp, then you can just assert it. You don't have it. It's true in the model. So that's one thing. I did not make a careful study of how much you could do without Sharp, but I mean, some of the things like the one that David mentioned about Sharp coinciding with double negation, obviously that you need Sharp to say that, and I don't remember exactly how much of the whether Sharp was used in sort of the what you can get out of excluded nibble, or probably you can do a lot without Sharp.
Okay, if there's no other questions, thanks, Mark. Okay. You want a break in half an hour?
I have a trivial postdoc question. Are we really stuck with the word crisp? I thought we decided we weren't going to use it. Oh, now everybody's using it.
I don't know if I was there when you said
I think I suppose how about just modal? Well, you said that word. Well, flat is good. You're attached to it now. Did you get attached to it? Okay.